Hey everyone, I'm Brad Potteiger, a senior researcher at the Johns Hopkins Applied Physics Lab. Today I'm excited to talk about our recent work on RUCKUS, a cybersecurity engine for performing autonomous cyber-physical vulnerability discovery at scale, addressing a key problem within the military and government cyber warfare space. I'd like to provide special thanks to my co-authors, Jacob Mills, Daniel Cohen, and Paul Velez, all at APL. Critical infrastructure is becoming digitized, relying on embedded and connected devices with increasing amounts of computational power, allowing for safety-critical operations to be performed on device as well as within the cloud. This shift to what is referred to as cyber-physical systems, or CPS, has revolutionized society, allowing safety-critical processes to be controlled by underlying embedded software, increasing the sophistication of control processes, while maintaining safety and reliability with easier user interaction. With this blessing also comes a curse. With increased connectivity, distributed architectures, and cloud computing, legacy software traditionally designed to be standalone is now becoming wide open to remote interaction. As such, these devices are becoming increasingly subject to cyber attacks, both domestically and by our foreign adversaries overseas. With a 146% increase in ransomware attacks we've seen over the last 4 months due to the shift to work from home, it's only a matter of time before these attacks become applicable to CPS, shutting down cities, crashing planes and satellites, and disrupting surgical procedures. To combat attacks within the CPS domain, active and dynamic defenses have been proposed and applied to safety-critical CPS within the government and military domain. My PhD work specifically over the last 5 years focused a lot on these adaptive defenses, leveraging moving target defense techniques such as instruction set, address space, and data space randomization within the application domain to mitigate memory corruption attacks that leverage common vulnerabilities in legacy software, such as buffer overflows. However, it's important to note that moving target defense techniques aren't just limited to the application, but can be applied to other layers as well, including examples such as software-defined networking and intelligent database sharding schemes. However, as I transitioned from my PhD from Vanderbilt last year to a more government-focused role at APL, my research has shifted to the other side of the coin, looking at the offensive side of cyber warfare. With all this work focused on moving target defenses, the primary question that comes up from an offensive perspective is how bad is this vulnerability problem really within the CPS domain? Specifically looking at how static configurations of systems can be leveraged to increase exploitation rates. In 2016, the DARPA Cyber Grand Challenge was a key case study for demonstrating the potential of autonomous exploitation techniques. However, one limitation of this effort is the narrow scope of the architecture that was focused on throughout this effort. When this technology is transitioned to the real world, a number of problems arise, most notably the problem with scale. One of the most popular case studies within CPS normally involves automotive applications, specifically autonomous vehicles, textbook examples of a domain that has shifted from a traditional standalone analog design to tech-heavy, distributed, and connected designs. With an estimated 100 million lines of code, most of which contains legacy software, third-party libraries, and publicly accessible mobile applications, there's a significant risk for remote exploitation. As such, it's no surprise that it was estimated that for every 100 lines of code, 5 contain vulnerabilities, within other estimates significantly higher. Furthermore, since software is homogeneous in nature on the same model of vehicles globally, if one vulnerability is found, exploits can be leveraged to generically compromise millions of the same model of vehicles around the world. In this paper, we specifically focus on one class of vulnerability that's popular within legacy applications, memory corruption vulnerabilities, of which buffer overflows are often the most publicly referenced. In this case, 3 types of attacks can occur: code injection attacks, in which payloads are executed directly; code reuse or return-oriented programming, where gadgets are chained together; and non-control data attacks, where adjacent variables are overridden. The threat model that we're going to leverage throughout the rest of the talk focuses on an automotive system with proprietary embedded firmware, leveraging a security through obscurity approach to minimize risk. Furthermore, there exists a communication interface such as cellular, Bluetooth, or Wi-Fi that allows adversaries to communicate with the infotainment center remotely, serving as an entry vector into the overall system. The vulnerability that we're looking at is specifically focused on a memory corruption vulnerability within the embedded firmware, and with common software between similar models around the world, it's estimated that this vulnerability could be scaled up. To recap, the problem that we're focusing on is motivated by the fact that even though security through obscurity approaches are common for protecting proprietary software within safety critical CPS, there's the potential vectors through open source libraries and third-party applications that, when compromised, could lead to the compromise of the whole proprietary system. The prime example of this is the Ripple 20 vulnerability disclosed at DEF CON. With a single vulnerability in the communication library, more than 100 million IoT devices were potentially vulnerable for the last decade. Furthermore, because the most impactful vulnerabilities are often the most common and obvious, the legacy aspect of CPS further complicates this issue and significantly increases the ease of pivoting throughout the network. As such, we see two main problems that arise from this situation. Number one, how do you speed up the time to reverse engineer safety critical CPS such as automobiles? And number two, how similar and at risk is proprietary software to open source library vulnerabilities? And how easy is it actually to scale up attacks? Our hypothesis is that by leveraging software similarity as a heuristic, we can significantly benefit our offensive efforts by significantly speeding up the time to reverse engineer and exploit software, much of which takes weeks to months to accomplish with a human-only approach under normal circumstances. To improve our reverse engineering speed and prove out our software similarity hypothesis, we present our developed architecture, RUCKUS, leveraging a hybrid human and autonomous approach to significantly speed up the time to exploit embedded firmware at scale. By leveraging this approach, we can leverage the best of both worlds, using human expertise for the fine-grained and in-depth analysis, while relying on autonomy for replication and scalability of the most high-level analysis. By using a heuristic focused on the similarity of software, we're taking the approach that the lowest hanging fruit should be analyzed first, aka the vulnerabilities in libraries that have already been found in previous reverse engineering efforts. As such, this allows us to find the easiest vulnerabilities first, saving significant time that would be spent starting the reverse engineering process from scratch. RUCKUS is comprised of three main components: a firmware discovery module, vulnerability discovery module, and correlation engine, all connected to a centralized database engine with a hybrid relational and graph analytics scheme. The first component in the RUCKUS architecture is the firmware discovery module. Since a vital key to the successes of our approach is a large data set of previously analyzed binaries and discovered vulnerabilities, it's critical to have an optimal method for automating data collection. This module has two modes, manual collection and automated collection. The manual collection provides input from reverse engineering teams that already create dozens of reverse engineering reports every week on safety critical infrastructure. The automated collection is also integrated with a web crawler capability to scan the internet and conduct high-level analysis on publicly discoverable firmware, allowing for rapidly accumulating large quantities of firmware metadata within our platform. After the firmware is collected, it's then carved to extract and pre-process the file system to identify binaries and files of interest. After the firmware is carved, and the output is then fed to the vulnerability discovery module for analysis. This approach is again split into two modes: manual inspection for fine-grained analysis and autonomous inspection where rapid high-level analysis can be conducted. Our vulnerability discovery process is split into three main steps: binary analysis, symbolic execution, and fuzzing. For binary analysis, we leverage Ghidra to disassemble, generate control flow graphs, and extract metadata such as symbols and function names from the binary. For symbolic execution, we leverage Anger to provide critical information for path exploration throughout the binary. Finally, we leverage a hybrid fuzzing approach based on cluster fuzz that relies upon symbolic execution output to direct the path exploration of the fuzzing program. The final component is the correlation engine. the key contributor to the heuristics leveraged within our architecture. The whole fundamental motivation for correlation is to be able to find similarities between pre-analyzed firmware and newly discovered firmware, rapidly giving hints of what the most likely vulnerabilities in files of systems are. We have three integrated techniques within our correlation approach: fuzzy hashing, dependency analysis, and natural language processing. First, fuzzy hashing is a popular technique for analyzing firmware images as a whole, but in this case, we can leverage this for finer grained similarity comparison of individual binary files within our firmware image. Second, dependency analysis allows for rapidly identifying open source and third-party libraries that contribute to the applications within the firmware, some of which have probably already been previously analyzed or publicly disclosed on the internet. The final technique is natural language processing, which we're able to leverage to compare various text and strings within the file system, such as file names, symbols, and function names. All three components of the RUCKUS architecture are tied together with a centralized database. This database uses a hybrid graph and relational storage structure approach to speed up the lookup time of queries. The graph portion of the database allows for storing high-level relationships, such as firmware similarity and file dependencies, while the relational portion is beneficial for storing bulk data, such as binary blobs and content like vulnerabilities and signatures. By using this approach, query time is significantly decreased compared to an individual graph database, while still providing the ability to answer the most popular relationship questions. To prove out our approach, we implemented a proof of concept of our RUCKUS architecture. Our specific implementation includes 7 main components: a web GUI for user interaction, web crawler for autonomous vulnerability discovery, file carver to extract the relevant binary files of interest, binary analysis tools, symbolic execution tools, fuzzing tools, and a custom developed correlation tool. It's important to note that we leverage both open source software such as Ghidra, Anger, and ClusterFuzz, while also leveraging specialized APL software such as CodeCut and Allstar, which provide large data sets of previously analyzed software package metadata. Additionally, within our implementation, we're able to create a specific process flow consistent with our overall architecture. In this case, the process is as follows. First, firmware is inserted into the pipeline either through a manual entry in the web application or autonomously collected from the web crawler. Next, the respective firmware is carved with binwalk and relevant binary and configuration files are extracted. Next, all the binary files are pushed to the vulnerability discovery module, where they're first autonomously analyzed for high-level metadata and vulnerabilities. Then the database is cross-checked to determine if there's any similar previously analyzed software that's contained within the firmware. If yes, then this information is given to the human reverse engineering team to start with when they start a more fine-grained analysis process. Finally, the output of the human reverse engineering process is stored within a centralized database for future reference. To evaluate our architecture, we put together a simple realistic scenario. Imagine hypothetically that a reverse engineering team was given a day to reverse engineer and discover vulnerabilities within an automobile that's critical to the success of a military mission and the safety of the warfighter overseas. Normally, as you can imagine, this process would take weeks to months to accomplish and would require significant resources. So under normal circumstances, this scenario would very likely not be successful. Now imagine that we have access to 20 open source firmware images from routers and 5 proprietary automotive firmware images, one of which is the image required for the mission. Furthermore, the routers have associated publicly disclosable CVEs, while the automotive firmware does not. In this scenario, we assume that we have no previous knowledge of the automotive firmware, while we have complete knowledge of the router firmware from previous reverse engineering efforts. To quickly go over the descriptive statistics of the router firmware dataset, we have access to 5 images each from 5 of the top router brands with a time frame from 2010 to 2020. There's three types of identified files within these images, consisting of shared libraries, configuration files, and executables. Finally, from a previous vulnerability discovery process, an average of approximately 12 vulnerabilities have been found per image associated with memory corruption vulnerabilities within the operating system. Now, when pushing the automotive data through the RUCKUS architecture, very interesting results were discovered. It's important to note that these 5 automotive firmware images are collectively contained in potentially millions of vehicles globally. So these vulnerabilities can scale not just for our mission, but could also be used by adversaries as well. Through the correlation module, we first found firmware images that weren't very highly correlated, which wasn't really unexpected starting out. However, what was interesting though, was that some router versions such as DD-WRT, Belkin, and to a certain extent Linksys, had a relatively high correlation with the automotive firmware, specifically with the shared libraries. As such, by using these sources, we were able to quickly discover vulnerabilities within the automotive firmware that took our reverse engineering time from around 8 days to 1.5 hours. The similarity of software is obviously beneficial for our reverse engineering objectives. However, from a defensive perspective, this is also very scary to realize the magnitude of this new vector. Essentially, this means that security through obscurity approaches are no longer effective, and adversaries can potentially blindly compromise safety-critical CPS through performing reconnaissance and analysis on open source and COTS devices. As such, for next-generation CPS systems, we see a need for more active and dynamic security defenses that make proprietary systems more unique compared to the open source community. I'd like to end by thanking everyone again for attending this talk, as well as my co-authors, Vanderbilt and APL, and will now open it up to any questions that you guys have.